All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're going to say, let's determine the center of gravity of our composite body that we're showing here. So we have a aluminum trapezoid and a bronze triangle here. All together, we're making a triangle out for everything on that. Center of gravity means that we are pulling in. We have differences in our specific weight or the densities in here. We need to account for that. So let's go ahead and go for it. In general, if we were looking at center of area in here, these differences would completely be ignored. Let's actually make a comment on that on the side. For center of area, center of area is going to ignore our changes in material. And we should just be able to say our center of area would then be a third of the way in, a third of the way up. Our center of area would be about right here. In the x direction, a third of 12 would be at 4. In the y direction, a third of 6 would be at 2. So we'll compare our final answer to that. How does accounting for the weight on this end up changing where we need to, or where we'd say the centroid, the center of gravity, is going to be at? And I'm going to label that even as COA, center of area. Let's come in and try to find our center of gravity. So if we're dealing with center of gravity, rather than just having an x bar is our x tilde a over the sum of our area, we're now pulling in weights. So our x bar we would write out as x bar is the sum of our x tilde w divided by our total weight, sum of our w. And we can do a similar thing for our y bar. Y bar should be the sum of y tilde w divided by our total weight. And then the last one that we can say is our weight on this, w, is just equal to our specific gravity, pounds per cubic inch. If I multiply by a volume, cubic inches, we will get to the weight. So W is gamma times the volume. We'll talk about that because we're giving areas right now. We'll talk about what we actually do then. But basically, in my shape, I need to still figure out how do I break this up. Our centroid tables typically don't have a trapezoid in them. There is a formula for a trapezoid, but it's really kind of convoluted and messy for everything. Instead, we can just shortcut that and say, you know, I could break this up into just into a triangle stuck on top of a rectangle and make 3 shapes out for this. So let's call our triangle the aluminum triangle, shape 1, our aluminum rectangle, shape 2, and our bronze triangle, shape 3. 3 pieces that we're setting up in here means I'm going to need 3 rows in my centroid table to actually get this solved out. And again, come in and make a table for these. It makes your work so much easier to follow. It's easier to check your work when something goes wrong than trying to put everything into one giant equation for this. It also builds towards, if you were doing this in a more in-depth thing, you'd probably be using Excel for it, and Excel naturally just puts everything into a table. So it's a good habit to get in. Let's start setting up our table. So we'll make our first column just be, what's the shape, or let's call them regions this time. What region am I looking at? And I need a row then for every piece I just broke that up into. So 1, 2, 3, and then we'll put in a summation. So region 1, our triangle, our aluminum triangle. Region 2, our aluminum rectangle. Region 3, our bronze triangle. And at the end of that, we'll also need to sum some things up. So we'll put in a summation row as well. Let's come in and let's do a volume column. Volume. And we'll get that in cubic inches. If we know our volume, let's go ahead and pull those gamma values into our table. So we'll put in gamma in here in pounds per cubic inch. And we'll set that up as another column. If I have volume and gamma, we said we can multiply them together to get the weight. Let's just make a weight column then. So our weight in pounds. And then from there, what else do I need? Well, I have x tilde, y tilde. Let's get a column for each of those. X tilde, this is the distance to the centroid of each individual piece. So put that in there in inches. And Y tilde, also in inches. And then the last two things I need, I'll multiply my X tilde times the weight and my Y tilde times the weight. So it's going to call for each of those. X tilde W, that will be in pound inches. And Y tilde W, Y tilde W, also in pound inches. But once we get through all of those, we can set up and find our centroids for everything. So we just need to fill in this table, which is going to be easier than it sounds. But what do? I'm given areas in here. I'm not given a depth on everything in this. Realistically, what's going to happen is that depth doesn't matter. I could assume any value other than 0, and my answer is going to come out to be the exact same if I'm just looking for X and Y coordinates on that. So let's assume anything. If we assume 1, it's the easiest. So assume a thickness of 1. So we'll write that off on the side too. Let's assume, we're assuming the thickness is 1. Assume our thickness equals 1 inch. But again, any number could get assumed there and we get to the same end result because that's kind of going to just drop away from everything. But let's go in and get our volume. So for piece 1, we have a triangle. The volume of a triangle should be the area times that thickness times 1. Or our volume is really going to be 1/2. Our base is 6. And our height, well, if I have gone halfway across this big triangle for my area, so halfway and 6 inches in, then I've also gone halfway up. So half of 6 is going to get me my height is 3. Times 3 times our area, or that thickness of 1. Is going to get me 9 cubic inches. For our second piece, shape 2, we're a rectangle, so our volume would be the area, base times height times that thickness. Our base is 6. Again, if we are halfway into the big triangle, we're halfway up. So 6 inches in means we're 3 inches up. 6 times 3 times 1 is 18. And our last one would be our bronze triangle. Is also a height of 3, a base of 6. So 1/2 base 6 times height 3 times our thickness 1 divided by 2 is going to get me also 9. I, for some reason, just wrote the formula differently. But if we were dealing with center of volume on this, I would want to sum up all of my volumes. I'm not, though. I'm just looking for center of weight. So I don't need to sum this column up. We'll skip over it. That gets us our gamma column. For gamma, I have both aluminum pieces. It's 0.1, 0.1, 0.1. And for the bronze piece, I'm at 0.3, 0.3. And in my centroid equations, that center of gravity equations, I don't have a sum of a gamma term in there. I don't need to sum this up. That same thing will be true. I need to sum the weight, but I don't need to sum X tilde or Y tilde. It's just these 3 columns will be the last ones for me to sum up. Let's get our weight. I know weight is gamma times V. 0.9 or 9 times 0.1 is 0.9. 18 times 0.1 is 1.8. 9 times 0.3 is 2.7. And adding that column up, I'll get my weight of this whole triangle is 5.4 pounds. From there, I can start getting my X tilde distances. That should measure from the y-axis to the centroid of every individual piece. Let's put those in a green. I'm just going to put a green dot for all of them. So for my rectangle, I'd be maybe somewhere about right here, right around where the center of area actually worked out, where I put the dot at least. For the triangle, we'd be 1/3 of the way in from that 90-degree corner, or somewhere where that dot showed up at. We are 1/3 of the way in from that 90 degrees, right there. Our bronze triangle, that same rule would apply. 1/3 of the way in from the 90-degree corner would get us right about there. So I need to measure for my X tilde distances from the y-axis to all 3 of those dots. So for that first shape, we're coming from the left edge of the rectangle to the middle of it. We're told That's just our base divided by 2 would be my x for this. So if that whole base is 6, x tilde will be 6 divided by, or if I'm looking at shape 1. Shape 1, let's do it first, would be a third of the way in from the 90-degree corner. Base divided by 3. The y-axis is at that 90-degree corner. I can directly apply this. 6 divided by 3 gets me to 2. For my next piece, the one that we started to talk through, I would be able to say, well, here it is. From the y-axis, I need to get to the middle of it. I can directly just do base divided by 2 because the left edge, where my centroid formula measures from, is on the y-axis. So 6 divided by 2 gets me 3 here. For shape 3, I need to go from that y-axis to a third of the way in. My centroid formula still measures from the 90-degree corner. So before I can apply the centroid formula, I need to get from the y-axis to the 90-degree corner. That's coming in 6 inches. So 6, and then I can add in. We keep going, so I add distance plus a third of the base, plus 6 divided by 3, or this is going to get me 6 plus 2, 8. And again, I don't need to sum that up. Then we can turn and go again to our 3 green dots. I'm measuring up in the y distance now. So for shape 1, I need to first go up 3 inches to get to where my centroid formula applies, and then a third of the way in. 6 plus 3 over 3 will get me to 4. For my second shape, I can go straight from the x-axis. It's already on the bottom of my shape. I'm measuring halfway in, so just half the height. 3 halves is 1.5. And for shape 3, again, I'm at that 90-degree corner for my x-axis, so I can go a third of the height. 3 thirds is 1. And from there, let's just multiply our columns together. X tilde times weight. 0.9 times 2 is 1.8. 3 times 1.8, our weight, and x tilde for shape 2 is 5.4. 2.7 times 8 is 21.6. And I do have a sum of my x tilde w. Let's add this column up. We'll get 28.8. And from there, I can get my y tilde w as well. Multiplying my y tilde times our weight. 0.9 times 4 is 3.6 pound-inches. 1.8 times 1.5 is 2.7 pound-inches. 2.7 times 1 is 2.7. And adding this column up, we get to 9. Which gives me enough, I can find my centroid. X bar should be my sum of my x tilde w, 28.8, divided by my total weight, 5.4. Or this is going to get us 5.33 inches. X bar equals 5.33 inches. 5.33 inches. And y bar, we can say, is y tilde w, 9, divided by 5.4. Our total weight, y tilde w, over the sum of our weight. Or y bar works out to be 1.67. Y bar equals 1.67 inches. So let's come back and compare that. If I were to label that, we are now at a center of gravity of 5.33, so almost all the way across the rectangle. 1.67, so a little bit less than halfway, or about halfway into just the rectangle, a little bit more than that. We're right around here. We'll put a blue dot at that point. Does that make sense that my center of area has shifted over and technically it's gone down a little bit? It should, because as we came in here, that center of area should have been a little bit higher. But it should, because really we're saying that bronze, the heavier section, is going to try to pull that center of gravity towards itself, from the center of area down to the centroid of the heaviest material, down here and the bronze section. Logically, that answer, whether the numbers exactly, we can't estimate, kind of what's happening there should make sense. If you're thinking of this as trying to balance an object, if we were trying to stick our finger down and it was all the same material, we could balance it right on the center of area. If we start having different materials in here, we'd want to put our finger closer to the centroid of just the heaviest material to actually get everything balanced. And that's really all that we're seeing in here. Doing the engineering and the math on it kind of verifies that. But hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Stick around, watch some more videos. Let's get you in A with JJ.